So now we're going to talk about the first and second fundamental theorems of calculus. So you might be familiar with the fundamental theorems of algebra. I think that's what they're called. These are the fundamental theorems of calculus. Very, very important to be familiar with. Extremely helpful. Let's jump into them. First fundamental theorem of calculus. Perhaps my most favorite theorem of calculus, and arguably one of the most important ones in calculus. This says, if we have f of x as a continuous function on the interval a to b, then capital F of x is the antiderivative of lowercase f of x. I know the notation's kind of annoying, where we have capital and lowercase, but that's actually by convention. We usually denote things as capital and lowercase when they're related by a derivative or an antiderivative. So then the first fundamental theorem of calculus states the integral from a to b of lowercase f of x dx is equal to capital F evaluated at b minus capital F evaluated at a. You might be like, okay, what? But this should really, really be exciting. If we just look at this integral here, I'm zooming in as much as I can, and I get rid of the bounds, and we were just left with this like integral of f of x dx. We know how to compute this. We have learned how to do it. This is just an indefinite integral. We know that the integral of f of x dx gives us its antiderivative, which we're calling to be capital F of x. And then we would throw in a plus c here. But now we're saying, with these bounds thrown in, we can still calculate its antiderivative as we did with indefinite integrals, and then evaluate this function at our bounds, b and a, and take their difference. And wow, we don't even need the plus c. The reason for that is if we plug in like b into this, we get f of b plus c. And then if we plug in a here, we get f of a plus c. And if we take the difference, we'll get like f of b plus c minus f of a plus c. And that's equal to f of b plus c minus f of a minus c. So the c's cancel, and we're left with f of b minus f of a. So the c's actually go away. But the great thing here is we can evaluate a definite integral in a very similar fashion to how we computed the indefinite integral. And the first fundamental theorem of calculus is used to find the exact area under the curve f of x from a to b. So we basically know how to compute the exact area under any curve, well, under most curves, from a to b. We have all the techniques to do that. We don't really need to learn anything new. We just have to remember this first fundamental theorem of calculus, and we can do it. We have all of the toolkit. We have all of the tools in our toolkit. We just got to apply it. So let's do it. So the integral from 0 to 3 of x squared dx. So by the first fundamental theorem of calculus, first fundamental theorem of calculus, the integral from 0 to 3 of x squared dx is equal to f of 3 minus f of 0, where f of x is the antiderivative of x squared. So how are we going to do this? F of x can be obtained by doing the integral of x squared dx, the indefinite integral. And we know that this, by the power rule, equals 1/3 x cubed plus c. Okay, so now let's plug in 3 and 0. And we can see that f of 3 minus f of 0 is equal to 1/3 3 cubed plus c minus 1/3 0 cubed plus c. That equals, let's see, 3 cubed is 27. 27 divided by 3 is 9. Plus c. 0 cubed is 0 times a third is still 0, and then this plus c stays. So we subtract a positive c, and then we're just left with 9. So that should be our answer, and in fact, it is. So before we move on from this example, there's a couple of things I want to point out. Perhaps first and foremost, something that might be mind-blowing to you, completely bizarre, or just something that you're like, I don't really care about this, but I think it's interesting. Let's consider the graph. That's not a straight line. Okay, I'm going to graph x squared. It looks something like this. That's a pretty bad drawing. But anyways, we look from 0 to some point here. This is 3, and this is the point 3, 9. This pink area, this weird shape, we said that that area is exactly equal to 9. Exactly equal to 9. Not like any fraction part, it's exactly 9. This weird random shape, I just think that's amazing, how that's exactly equal to 9. It's crazy. But anyways, with that said, let me just erase this so I have some room. We don't really want to write all of this out all of the time. So I'm just going to introduce some notation of how we can do this. So how we're going to do it going forward is we'll say that the integral from 0 to 3 x squared dx, what we'll do is we'll ignore the limits for now. We'll just pretend it's an indefinite integral. So the indefinite integral of x squared is 1/3 x cubed plus c, but we will actually omit the plus c because we know that's going to go away. And then we reintroduce the limits, and the way we do this notationally is we draw a bar like this, and we draw the top limit at the top and then the bottom limit at the bottom. So we're saying the integral from 0 to 3 of x squared dx is 1/3 x cubed bar 3, 0. Now this, we can't leave our answer like this, we still have to evaluate it. But basically what this is saying is that this is our antiderivative. We're going to plug this into here, and then we're going to plug this into here and take their difference. So what this is equivalent to is 1/3 3 cubed minus 1/3 0 cubed, which is equal to 27 over 3 minus 0, which is equal to 9. So this is like the sort of notation I'm going to use going forward. I don't want to like spend time rewriting this in terms of an indefinite integral. We should be able to see that this is basically the same process. We treat the integral as an indefinite integral at first, then reintroduce our limits, because our limits only come into play when we're computing the function evaluated at those limits, and then we just plug them in and take their difference. With that said, let's try to evaluate this definite integral. So we have the integral from 0 to 4 of x square root of x plus 2 dx. And so the way we can do this is we can treat square root of x as x to the 1/2 power plus 2 dx. And then we're just going to integrate this as normal without worrying about the limits. So this is equal to, for x squared, we use the power rule. So we add 1 to the exponent, which makes it 3/2, and then we divide by that exponent. So dividing by 3/2 is the same thing as multiplying by 2/3. 2/3 x to the 3/2 plus integral of 2 is 2x. And we don't need to worry about adding the plus c, but let's add back in our limit. So we put the bar 4, 0. And now we want to evaluate this entire function at 4, evaluate the entire function at 0, and take its difference. So that would be equal to 2/3 4 to the 3/2 plus 2 times 4. And then we subtract the same thing, just evaluated at 0 this time, plus 2 times 0. So that should be our answer. Let's simplify it just for the fun of it. Let's go back to front. 2 times 0 is 0, so that goes to 0. 0 to the 3/2 power is 0. and 2/3 times 0 is still 0. So this entire term goes to 0. So then we're just left with this left term. 2 times 4 is 8, so we'll have plus 8. 4 to the 3 halves power. So the way we do that is we take 4 to the 1/2 power, which is 2. Square root of 4 is 2. And then we cube 2, so that's 8. And then 2/3 of 8 is 16/3. So this will be equal to 16/3 plus 8. And then adding these together, we get 40/3. So once again, it should be kind of interesting that such a strange function, square root of x plus 2, which looks something like that, I suppose. The integral from 0 to 4, so this entire red area, that comes out to this 40/3 value. Such a nice fraction. It's crazy. It's crazy. Okay, so congratulations, we've evaluated 2 definite integrals. Pat yourself on the back. This is difficult stuff, so yeah. And this is a very difficult question that we're going to move on to. We have the integral from 1 to 4 of 3 minus absolute value of x minus 3 dx. I'll be brutally honest. Absolute value functions are terrible. They're so annoying to work with. And the reason for that is they're not smooth. So when we think about functions normally, when we think about sine of x, which looks something like this, that's a pretty bad drawing, or like x squared, which looks something like this, or x cubed, these are all smooth functions. As you travel along it, it's a very smooth journey. With the absolute value of x, that looks like this. That's not a very smooth journey. Well, it's smooth if you go along this way, but then you reach this corner here. And that's not very fun to work with. So, with absolute value functions, it's very helpful to draw a graph. And remember that absolute value functions are basically piecewise functions. So let's just take a look at the one that I've drawn. I've drawn f of x equals the absolute value of x in this case. And it's piecewise in that we can say that for x greater than or equal to 0, f of x, let me write f of x. Well, what is the absolute value of x when x is greater than 0? If x is like 10, then the absolute value of 10 is 10. If x is 27, absolute value of x is 27. So absolute value of x when x is greater than or equal to 0 is just x, right? And that's represented by this line here. That is the graph of the line y equals x. So that's that part of the function. But when x is less than 0, we're on this line here. So f of like negative 3 is equal to 3. F of negative 10 is equal to negative 10. So here we return negative x. And indeed, that is the line negative x. So we've split the function up into pieces. And these functions are much easier to like integrate if we need to. We don't really know how to integrate that, but we can deal with this. So it's helpful to draw a picture and then define it piecewise. So we want to first draw the picture of the function we're given, which is 3 minus absolute value x minus 3. So let's do our best attempt at drawing it. The way I like to do it is probably not the best way of doing it, but it gives a good idea of like how to, come up with a sketch. So I'm just going to consider what happens when x equals 0. When x equals 0, the function here, x minus 3 is negative 3. So the absolute value of negative 3 is 3. 3 minus 3 is equal to 0. So at x equals 0, we're at the origin. What about x equals 1? Well, there, this evaluates to 2. The absolute value is 2. 3 minus 2 is 1. So we're somewhere here. When x equals 2, this evaluates to 1. 3 minus 1 is 2. So at 2, we're at 2. At x equals 3, this goes to 0. 3 minus 0 is 3, so we're somewhere up here. X equals 4, this goes to 1. 3 minus 1 is 2. So we come back down here, and you can continue doing this, and you'll see that the graph looks something along the lines of this. And I guess a better way of thinking about it is that there's some shifting of the absolute value graph. So we take you can consider the graph negative absolute value of x, and what we're doing is we're shifting it right by 3 and we're shifting it up by 3. So this shifts it upwards by 3 and this shifts it to the right by 3. That's the better way of thinking about it, but in case you're not too comfortable with that, this is a fine way of doing it as well, though you want to ensure that you're correct about what you're drawing. Okay, so that's sort of our drawing, and we should probably define our function piecewise. So f of x equals 3 minus absolute value x minus 3. And so where is really the turning point? I guess I'm giving it away, but it's at x equals 3. That's where our corner is, and that's where we change the lines that we're traveling on. So we want to consider when x is less than or equal to 3, and when x is greater than 3. So when x is less than or equal to 3, we're on this line, and this is the point 0, 0, this is the point 3, 3. I should write that down. So that is the line of x. And then here, when we're greater than 3, we're on this line. So we know one point on the line is 3, 3. We should find another point on the line. So perhaps, let's see where it intersects the x-axis. So we would want 3 minus this value to be equal to 0. So we want negative absolute value of this to be negative 3. We want the absolute value of x minus 3 to be equal to 3. So that means x either equals 6 or 0. We already know at 0 it intersects the x-axis. So the other point is 6. So this would be 6, 0. So now we have 2 points on that line. And we can, use our knowledge of how to find the equation of the line, but we'll just give it, that's 6 minus x. Great. So we've evaluated the function piecewise. Now, why did we do that? We're curious of the integral from 1 to 4. So the area under the curve from 1 to 4. So 1 is somewhere here, this is 1, and this is 4. So we want this blue area here, and as we can see, remember the area is bounded by the function and the x-axis. So from 1 to 3, we're bounded by one line, but from 3 to 4 we switch which line we're bounded by. So we need that piecewise definition. So all of that to say, we can say the integral from 1 to 4 of 3 minus, here, dx, we want to split it up at 3, so our first integral will go from 1 to 3. And then our second integral will go from 3 to 4. And now it's just a matter about which function are we bounded by. From 1 to 3, we're bounded by this line, which we said was equal to x. So we throw in an x here. And then from 3 to 4, we're bounded by this line, which we said was 6 minus x. So that would go in here. And then we can evaluate these integrals. So this is going to be equal to integral of x is 1/2 x squared, evaluated 3 to 1. And then integral of 6 minus x, integral of 6 is 6x, minus 1/2 x squared, evaluated from 4 to 3. And then we have to do these individually, and then we'll combine them together. So for the first term, we plug in 2 squared, and then we subtract when we plug in 1 squared. And then we do the same thing for the right term. First we plug in a 4 squared, and then we subtract the same thing but with a 3 in it. 1/2 3 squared. And then we can compute this out. This comes out to be 2 minus 1/2 plus, the first term is what? 24 minus 8 minus 18 minus 9/2. And I'm not going to do that right now. Wait, did I do something incorrectly here? Oh yeah. This went from 3 to 1. So this should be a 3 here. So this is a 3, and then that becomes 9/2. And then if we do this, we get 6.5. Now this is actually a fun one to check. And we can do it with geometry because the area is pretty much like, it's a pentagon, but we can obtain it quite easily. And I'll very quickly prove that we got the correct answer. To get the blue area, we can find the area of this triangle, and then from that subtract this triangle and this triangle. So at 1, we're at the point 1, comma, if we plug 1 into here or here, we're at 1, 1. And then at 4, we're at 4, 2. So the area of the big triangle is equal to 1/2 times 6 times 3 base times height. So that's going to be equal to 9. Then we'll find this triangle. That's going to be equal to 1/2 times 1 times 1, which is equal to 1/2. And then the other small triangle, that's going to be equal to 1/2 times 2, which is equal to 2. And we can see 9 minus this sum. So 9 minus 2.5 is equal to 6.5, and that's exactly what we got. So in one sense, absolute values are annoying because we have to split it up into 2 separate functions. But on the other hand, they're good because they're easy to check. So yeah, this is a fun question. We got to do it with geometry and also with some techniques that we've learned. Cool, let us continue onward, and here we go, seeing some trig functions. The integral from 0 to 2 pi of sine of x dx. So let's just do it. Integral from 0 to 2 pi of sine of x dx. Well, if we ignore the limits and we just treat it as an indefinite integral, the integral of sine of x is equal to negative cosine of x. And then we reintroduce our limits going from 2 pi to 0. And then we evaluate it using the first fundamental theorem of calculus and take the difference. Okay? Cosine of 2 pi is 1, so negative of that is negative 1. Cosine of 0 is also 1, so negative cosine of 0 is equal to negative 1. Negative 1 minus negative 1 equals 0. Interesting. And once again, let's connect it back to geometry. Let's sketch what does sine of x look like. So this is my x-axis, this is my y-axis, and this is going to be a very bad drawing, but it looks something like this, where this is at 0, here we're at 2 pi. And we're trying to find the area from 0 to 2 pi. So we're trying to find the total pink area. And sure enough, this area above the curve is equal to the area below the curve. They just have different signs, so they cancel each other out, and we're left with 0. So once again, relating it back to geometry. This is a thing that you should be doing a lot. Thinking about how does this computation relate to the area under the curve. Not only will this help confirm your answer, but it will give us some good habits going onwards of really understanding what integrals are doing. Cool. Do a quick word on physics. We did a couple of problems about it, but let's just write it out. So we said velocity is the derivative of acceleration, so surely acceleration should be the antiderivative of velocity. And sure enough it is. If we take the integral of acceleration of some, like a function that describes acceleration in terms of t, we take it from a to b, then that is equal to the velocity at point b minus the velocity at point a. Same sort of relationship with velocity and position. So this would be like displacement. So just writing them out, but we kind of already deduced this in an earlier video. Okay, the mean value theorem. One of the most important, or the most common theorem discussed in this class. I don't know if I'd call it the most important, but it's a very, very popular one to be discussed. And it's quite amazing that it's true. Let me just quickly hydrate. Oh no. Okay. Let's see. So, mean value theorem. The integration version. I think we discussed it with derivatives? Yeah, I think we did. But this is the integration version. So we have f of x, which is a continuous function on some interval. So then by this theorem, there has to be some point c within the interval a to b, such that the integral from a to b of the function, so the area under the curve, is equal to the function evaluated at c times the difference of the limits of the interval. So that's saying there's some point c in the interval such that f of c times the width of the interval is equivalent to the area under the curve within that interval. Why is this so amazing? Well, let's take a look at this graph. This is the integral from like a to b of this function, right? This big area here. That is the integral. The mean value theorem is saying there's some point within this interval where if we trace it upwards and we get to the function value at that point, then we can create a rectangle where the rectangle, its width is defined by the interval and its height is defined by the function evaluated at that point in between. And if we take the area of that rectangle's area will be identical to the area underneath the curve. Crazy. We're smushing this area, we're like condensing it into a rectangle. And the weirdest way to think about it is like, imagine this, I just thought about this now, but maybe it'll help you. Imagine this as like a chunk of cheese or something, and you're like morphing the chunk of cheese into a rectangle such that it has this width. It's basically saying like it's always possible. We can always chunk it into that rectangle. I don't know how I thought about that, but maybe that helps you think about it. So this is the mean value theorem integration version. Now we have the average value of a function. This is super handy. A lot of times we're asked, what is the average value of a function on an interval? And we can now find it. So if we have some function on some interval a to b, then the average value is given by 1 over the size of the interval times the integral from a to b of that curve. Okay, do I have a good explanation for that? No, not really. I guess it's just taking the area underneath the entire curve, and then we multiply it by the width, which is sort of like dividing by the sum if we're taking averages of numbers or something like that. So that's sort of how you can think about it. With that said, let's try to find the average value of f of x equals sine of x plus cosine of x on this interval. So let's just rewrite the formula. The average value of f of x on a to b is equal to 1 over b minus a times the integral from a to b of f of x dx. So let's just plug in the values given in the question. So that would be 1 over, the interval is from 0 to pi, so this would be pi minus 0, times the integral from 0 to pi of sine of x plus cosine of x dx. So that's equal to 1 over pi times that integral. So we can treat this as an indefinite integral, then we'll reintroduce the limits. So integral of sine of x is negative cosine of x. And the integral of cosine of x is sine of x, so we add sine of x. And we're going to evaluate this at pi and 0. So this will be equal to 1 over pi times negative cosine of pi plus sine of pi minus negative cosine of 0 plus sine of 0. Okay, and then we can evaluate this a little bit. 1 over pi, we have to remember some of our trig techniques. So negative cosine of pi. Cosine of pi, I believe, is negative 1. So negative cosine of that is positive 1. I don't need the parentheses. Actually, I do. Sine of pi, that's equal to 0. I know that. Cosine of 0 is 1. So negative cosine 0 is negative 1. Sine of 0 is equal to 0. So that's equal to 1 over pi times 1 plus 1, which is equal to 2 over pi. I don't feel like sketching this sine x plus cosine x because that'll take me just a couple moments. I don't want to really do that. But perhaps you can convince yourself of why that's true. Maybe plug this graph into your favorite graphing calculator or graphing app and just see does it seem like the average value of the function is 2 over pi? If we were to draw that line, does it seem like that's the average value of the function? Try it out for yourself and hopefully that's true. In fact, it is true. Okay, and at last, long awaited, we're now going to discuss the second fundamental theorem of calculus. So we talked about the first fundamental theorem, now we got to talk about the second fundamental theorem. Okay, so f is a continuous function and c is a constant. Then there exists a unique antiderivative of f, which we call capital F, such that f of c equals 0, and f of x is equal to the integral from c to x of lowercase f of t dt. That sounds very complex, and certainly it is. But at least this first part should be relatively clear. We understand that there are many, many antiderivatives of a function because of that plus c term. But surely there's got to be only one constant that would make the antiderivative equal to 0 at that point, right? If we have multiple functions that evaluate to 0, then they would all be the same function. This is a little bit more complex. But this is saying the antiderivative at some point x is equal to the integral from this point c that we start out with, this constant value, to x of this function, but in terms of t. So we kind of do a change of variables there. And we'll probably see this with an example in just a moment. But really, the implications of this theorem are really what matter. So the following are implied from this theorem of calculus. And this says for every x in an interval, the derivative of the integral of from a to x of f of t dt is equal to f of x. So we have a derivative and an integral, and basically what this is saying is that these sort of cancel out, and we just have to evaluate f at this x. So there's sort of like a cancellation going on, which kind of makes sense because one's a derivative, one's an antiderivative. However, if the upper limit is a function, then the derivative of the integral from a to g of x this time, of f of t dt, it's pretty much the same thing. F of g of x, so we plug in that upper limit, similar to what we did here, except now we have to multiply it by the first derivative of it. So this could kind of be reminiscent of the chain rule. In fact, I wrote it there. I didn't even realize that until now. And lastly, another very important fact is that if we swap the limits of integration, the integrals are the same in size, we just have to have a negative sign introduced. So flipping the limits flips the sign of the integral. So these are kind of the properties we want to be familiar with. Wonderful. So, using the properties that we just learned, we want to evaluate this limit, which I'm not going to read out. So, we have like a function as a limit, And we should remember there's a property of when function is the top limit, right? That's the second property right here. So we can get this to be at the top by swapping these two limits. And we know that there's a property for that. So the derivative of the integral from sine of x to 2 of cosine of t plus 2 dt is equal to the derivative of a negative, now we swap the limits, cosine of t plus 2 dt, right? So that's what we're used to. And now we can further evaluate this, but let's recall what the chain rule definition was. Property 2 told us that d dx of a to g of x of f of t dt is equal to f of g of x times g prime of x. So, with that said, this up here is going to be equal to this function here, evaluated at sine of x, times the derivative of sine of x. Okay, so that's going to be equal to cosine of sine of x plus 2. So that is this function evaluated at sine of x times the derivative of sine of x, which is cosine of x. But then we also had this minus sign here, so we have to throw that in there. And then we can further evaluate this. That'll come out to negative cosine of sine of x. No, that's not completely right. This would be negative cosine of x times cosine of sine of x minus 2 cosine of x. So a little bit nasty, but that's our answer. So now we can kind of start to handle antiderivative or integrals with functions as its limit. It's a little bit messy, but once we become familiar with these properties, it's a little bit more of a breeze. Let's do another one. So we want to find this. We want to find the derivative of this integral, and notice how now we have two functions. So that's kind of annoying. So how are we going to do this? Well, what we'll do is we will note that we're trying to find the derivative of this first of all. So let's write that out. 1 over 2t dt. And we kind of want to apply property 2 because we have functions as the limits. But property 2 only works when the top limit is a function and the bottom one is a constant. So we kind of have to get rid of this one or make that a constant. And the way we're going to do that is we're going to split up the integral. We're going to say that this is equal to the derivative of the integral from x to a of 1 over 2t dt plus the integral from a to x squared of 1 over 2t dt. Let's take a brief moment to understand why we can do this. First of all, we'll say that a is a constant because we want it to be a constant for us to use property 2. Secondly, are we certain that there's an a in between x and x squared? Yes. The reason for that is because x is greater than 0. So it's not going to be the case that they're the same value unless we get to 1. Maybe the bound should be 1. Let me just change this to 1. That'll make a little bit more sense. Right? Because once we surpass 1, if we were to graph this, x looks something like this, x squared looks like this. Let me just draw it a little bit better, actually. Right? This is the point 1. Once we surpass 1, this is x squared. There's always some distance between them, so there is some value in between them. It's a pretty bad explanation, but you can convince yourself of why that's the case, that we can indeed split it up like this. And so now we're kind of chilling. This derivative can like distribute into each of these, and we're able to compute this one quite easily because we have a function at the top, but and a constant at the bottom. But this one we have a constant at the bottom and a function, or constant at the top, function at the bottom. So we can swap those two limits. So what we're going to say is that this is equal to negative integral from a to x of 1 over 2t dt plus the integral from a to x squared of 1 over 2t dt. And what I'm just going to do is I'm going to just rearrange these a little bit. We'll bring this one over here, change this to a minus sign, and then put this one here. Right, that's the same thing, just a little bit cleaner. And then we can sort of like distribute the derivative, just because that's how derivatives work. They distribute over like addition, d dx of, sorry, we should be subtracting here, integral a to x of 1 over 2t dt. And now we're able to use the second fundamental theorem of calculus implications. So this will be equal to this function evaluated at x squared times the derivative of that. So that would be 1 over 2 times x squared times 2x minus 1 over 2t evaluated at x times the derivative of x. So this would be 1 over 2x times 1. So this is equal to 1 over x minus 1 over 2x. And that should be our answer. Okay. Great. So yeah, just be familiar with these three properties. Super helpful. Okay. I think we'll stop there for today.